Newton's third law states that when water is expelled from a rocket nozzle, the nozzle experiences an equal and opposite thrust, propelling the rocket upward. In water rockets, water serves as the reactive mass, while compressed air above it stores energy for accelerating it. The impulse of the rocket is the product of thrust and its duration. Increasing the water fraction can increase total impulse by expelling more mass, but it reduces the air, lowering the energy for acceleration and thrust. Increasing mass can harm overall rocket performance if it outweighs the impulse gain, so an optimal ratio is essential for effective propulsion. So initially we first put ideas to paper before completing some CAD drawings and getting some 3D renderings. We then proceeded to laser cut, and here we're just cleaning off the actual parts and then gluing it to the plastic chamber. By using bubble wrap, we can increase the contact time during any collision and reduce the force applied to the egg. After several design iterations, we came across using air flaps in order to release the nose. However, using them in the midsection proved to be unfruitful due to the lack of airflow. So by moving this down towards the bottom of the nose cone, it would allow for a quick release. After further deliberation, we decided to use the plastic bottle due to the surface finish as well as the lightweight material and effective aerodynamics. The stability of a rocket depends on the center of pressure relative to the center of mass. As the center of pressure moves down the rocket, the fin size increases, helping keep the rocket stable. However, larger fins can increase instability during crosswinds. By using fins that are long and thin, we can allow the rocket to remain stable in high winds as well as help stabilize it during the change in pressure. In order to create an effective parachute and increase drag, we opted for an octagonal parachute in order to allow symmetry. Since terminal velocity is inversely proportional to the square root of drag, the larger the drag, the slower the descent. Introducing a slip hole allows air to flow through the center, preventing spillages from the side, allowing greater stability. The pilot chute uses glued ridges for plastic memory to ensure that it opens up correctly and allow our main parachute to deploy. By using CAD for our rocket, we were able to design and ensure that all the parts would fit together smoothly, as well as using the simulation to get the required measurements and dimensions for the fins and water fraction ratio.